Hi, Year 11. This is our second lesson for the topic of probability for the International Baccalaureate DP courses, Analysis and Approaches, and Applications and Interpretations. And in this lesson, we're going to cover the laws of probability. So let's start with the difference between experimental probability and theoretical probability. Experimental probability, or relative frequency as it's called in statistics, is based on the outcomes of a series of experiments. So we use this formula. Probability that event E occurs is equal to the number of times E occurred divided by the total number of trials. So for example, if I toss a coin 400 times and it lands tails 211 times, then the probability that it landed tails is equal to 211 divided by 400. Whereas theoretical probability is the chance that a particular event will occur based on the number of possibilities for the event and the experiment. So it's the probability the event will occur in theory. It's a very similar formula. Probability that E will occur is equal to the number of ways E can occur divided by the total number of possible outcomes. And from last lesson, we learnt that this is the same as the number of elements in the set E divided by the number of elements in the sample space. Here's an example. A die has the numbers 1, 2, 3, 4, 5, 6. If the die is tossed once, find the probability that a 6 is thrown. So there is one way we can get a 6 out of 6 possible outcomes, so the probability is 1/6. Now last lesson we learnt that the complement of a set contains all of the elements not in the set. And in the same vein, a complementary event is the opposite of the event. It's the probability the event doesn't happen. And not surprisingly, we write the probability of E graph. Now, it's important to note that the probability of E occurring plus the probability of the complement of E occurring must equal 1. Here's an example. A 6-sided die is tossed to find the probability that we throw a 5. That, of course, is 1 out of 6. Find the probability that we don't throw a 5. That has to be 5 out of 6. Now, so far we've covered simple events, and that's where only one thing occurs, like drawing a card from a standard deck and noting its suit. A compound event is the combination of two or more simple events, so we could have drawing a card, noting its colour and its suit, tossing a coin and a die, drawing two cards from a standard deck and noting the colour. Now we have two laws of probability. We have the multiplication law and we have the addition law. The multiplication law states that the probability of A intersection B, or A and B, is equal to the probability of A multiplied by the probability of B. Now, it is only for independent events, and we haven't covered this yet. We're going to do a whole lesson on this. So I'm only going to use this law when we're doing tree diagrams later in the lesson. The addition law, it states that the probability of A union B, or A or B or both, is equal to the probability of A plus the probability of B, take away the probability of A intersection B. Now it's important to note that if we have mutually exclusive events, in other words, there's no overlap between the two circles in a Venn diagram, no common elements, then this intersection is 0, and so our formula will be just reduced to the probability of A plus the probability of B. Example 1. An 8-sided die bearing the numbers 1 to 8 is thrown. Let A be the event that an even number is thrown. Let B be the event that a number greater than 5 is thrown. So let's start with a Venn diagram. We have overlapping circles because we've got common elements. And those common elements are even numbers greater than 5, so 6 and 8. Filling in set A, we have got even numbers, so we need a 2 and a 4. Filling in set B, we have got numbers greater than but not equal to 5, so we're missing a 7. And we've also got numbers outside those two circles. We have 5, 3, and 1. Now, the probability of A union B is equal to the probability of A plus the probability of B, take away the probability of A intersection B. In other words, 4 eighths plus 3 eighths take away 2 eighths, which is 5 eighths. Now, you're probably thinking, isn't that a bit of overkill? Why do we even need the formula? It's obvious from the diagram that there are 5 elements here out of 8, and that is true. But you need to know how to use this formula in case you're given a question without any context. Like in this example, let the probability of A equals 0.16 and the probability of A intersection B equals 0.1 and the probability of the complement of B equals 0.36. We need to find the probability of A intersection B graph. Now remember, that's one of those cookie regions. Let's draw up a Venn diagram and see what we can figure out. So we've got overlapping sets, A and B. What do we know? We know the intersection is 0.1, so let's put that in. Now if we want to find the probability of A intersection B graph, that's this part here. Now we know the probability of A is 0.16. If we take away 0.1, we're going to know the probability of just A. Part B, let's find the probability of the complement of A union B. So that means everything outside those two circles. All right, what do we know? We know the probability of the complement of B is 0.36. So outside of B is 0.36. If we take away the 0.06, that is just A, we're going to get the probability of the complement of A union B. So that is 0.36 take away 0.06, which is 0.3. And then finally, let's find the probability of B intersection A graph. Again, that's a cookie region, but it's this one. And we know all of these probabilities are going to add to 1. So all we need to do is 1 take away 0.06, take away 0.1, take away 0.3, which is 0.54. And that's the answer. A two-way table is another way of representing data from compound events. It's really similar to a Venn diagram. Here's the data from a class of 30 students who study chemistry and or biology. And if you have a look at the table, it's pretty clear. Here we have 5 students who study both biology and chemistry. Here we've got 15 who study biology but not chemistry. So if we ask a question like this, let's find the probability that a student selected at random studies only chemistry. We've just got to find that part in the table. So only chemistry means chemistry and not biology. So chemistry and not biology, there are 10 out of 30. So the probability is 1/3. Now a multi-stage event, it's a compound event, but the 2 or more events occur in sequence. For example, we might draw 2 raffle tickets, or we might choose 2 chocolates from a box, or we might note the sex of 3 children in a family. And a tree diagram is a really good way to organise outcomes for multi-stage events. So here we've got the sex of the eldest 2 children in a family. Here's the first child, boy or girl. Here's the second child. And you can see how I've drawn the same outcomes off each of the outcomes in the first event or stage. Now in the previous example we had equally likely outcomes, 50-50 for boy or girl. But if the outcome probabilities are not equally likely, we create a probability tree and we write the probabilities of the outcomes on the arms. Here's an example. The probability that it will snow on any given day is 90%. So we're going to have a look at the probability of snow and not snow on 2 consecutive days. It's going to have the same structure. You can see we've got snow and not snow here, so that's the first day, and snow and not snow here for the second day. And here I've got 90% chance of snowing and 10% chance of not snowing. Now we're going to look at using the multiplication law and the addition law with a probability tree diagram. So let's find the probability that it will snow both days. The first thing to do is to figure out where that is on the diagram. Here's that it snows on the first day, and here it is that it snows on the second day, so we want this. Now, as we're going across the tree, we're going to multiply. So we're going to say the probability that it snows the first day times the probability that it snows on the second day. So there's our answer. It's 81%. And I suggest you write this down. When we're going across the tree, we multiply, because in probability the word and means times. So we want the probability that it snows on the first day and it snows on the second day. Now let's look at our addition law. We're going to find the probability that it will snow on exactly one day. So again, let's locate that on the diagram. So exactly one day means it either snows the first day and not the second, or it doesn't snow the first day and then it snows the second day. So we want this. So as we go across the tree, we're going to times, and here's the new rule. As we go down the tree, we're going to add. So here's our answer. So this is the probability it snows, then doesn't snow, plus probability it doesn't snow and then snows is equal to. So there's my multiplication law, there's my addition law. And so that's 18%. And here's a new rule for you. When we go down the tree, we add, because in probability, or means plus. So let's have a think about what I said before. The probability that snows and then doesn't snow, or probability that it doesn't snow and then snows. Now you might be wondering why we didn't use the full rule. We just used the first two parts. Can you see that? We didn't ever take away the probability of the intersection between the two events. And the reason is these are mutually exclusive. So as soon as it snows on a particular day, we call it a snow day. And you can't have it snowing and not snowing at the same time. So the probability of the intersection between those two events is 0. Okay, last thing for this lesson. When the events in a multi-stage experiment are the same type of sampling event, that means you're drawing something out of a bag, for example, we must consider whether there is replacement or non-replacement after the first event, because this is going to affect the probabilities for the second event. So for example, if Sam chooses 2 counters from a bag containing 3 blue and 4 white counters, we're fine with the probabilities for the first event. They are 3/7 and 4/7, but we don't know the probabilities for the second event until we're told whether she replaces the first counter or not. Now, if Sam replaces the first counter after it's drawn, then these probabilities here are going to be exactly the same as these. What is the probability that she draws 2 white counters? Let's find that on the diagram. It's here and here. As we go across the tree, we multiply. So probability of white and white is 4/7 times 4/7, which is 16/49. But if Sam does not replace the first counter after it's drawn, then these probabilities are going to be very different, and they're not going to be the same. So let's start with this case. A blue is drawn first. So that means instead of being 3 blues, when we get to this point here, there's only going to be 2 left out of 6 counters altogether. However, there are still 4 white counters, so this probability here is going to be 4/6. Now these numbers will always add to 1, and they do, so that's a quick check for you. Now looking down here, this time we had a white drawn the first time, so there are still 3 blues left out of 6. However, there are only 3 whites left out of 6, and quick check, yes, they add to 1. What is the probability that she draws at least 1 blue counter? So that could be blue and blue, or blue and white, or white and blue. And you can do that if you want to. You can do all 3 paths and add them up. But it's much easier to do the complementary event. So in other words, 1, take away the thing you don't want, which is this one down here. So 1 take away white, white. As we go across the tree, we multiply. So 1 take away 4/7 times 3/6, which is 30/42, which reduces to 5/7. And that's it for this lesson. Our next lesson is on conditional probability.